we have Dr. Kathy So from the Ethereum Foundation. Today she's going to talk to us about ZKML, Zero Knowledge Machine Learning. Something particularly alien to me, both zero knowledge and machine learning, but I think it's going to be very exciting. Huge, huge things to come from the privacy space, from the machine learning space, and how this can be leveraged for DeSci. I'm very excited to find out. So thank you very much.
Yeah, so thank you for inviting me here. Thank you, George, for organizing this. So just before I start, a little bit of introduction, just so that everyone will feel a little bit more relatable. Before I actually joined Web3, I was in academia. In fact, I got my PhD in cognitive psychology. So I was a heavy machine learning person. It's all about data science, machine learning. I actually knew nothing about crypto. But then I got really excited when my PhD advisor is like, well, I have this friend from crypto space. They are doing something that is like zero knowledge. Like, have you heard of this? Do you know what this is? So then I hopped into the zero knowledge space. And slowly I found out that, well, there's actually a lot of things that you can do at the intersection between zero knowledge and machine learning. Right, so as George said, ZKML is zero knowledge machine learning. So there's two parts to it, zero knowledge and machine learning. And first of all, I will explain what is ZK, and then ZKML. And then we'll talk about some use cases of what is ZKML going to do for decentralized science. And then a little bit of how to get involved if you're interested in this space. Right, so first of all, what the heck is zero knowledge proof? Right, I think it's quite alien, especially to a lot of people who are not already in the crypto space right now. Even if you're in the crypto space, not everyone understands what zero knowledge proof is. So in essence, this is the process when we talk about zero knowledge proof. Okay, so you have an entity that is called the prover. So the prover is on the left. The verifier is the person on the right. Right, when we say person, really is an entity or a machine. So the idea is the prover would be like, well, I got maybe a solution to a problem or an answer to a math question. I want to prove to you that I know it. Okay, and then what the prover on the left would do is to make a proof. So the idea is you can make a mathematical proof that embeds that information, and then you can send the proof to the verifier. And then the verifier will be able to check the proof. Okay, so in practice, this verifier is actually just a smart contract. Okay, so you put in a few numbers into a smart contract. The smart contract will be like, okay, good, valid proof, or bad, invalid proof. So, well, not just that as a proof, there is also certain properties of this zero knowledge proof, which is, usually we talk about 3 properties. There's a 4th one on the next slide, which is incredibly important, although mathematically we don't consider it a property. So the idea is you have completeness, soundness, and zero knowledge. So completeness, the idea is you wouldn't have false negative, right? So if your proof is real, is valid, you will never get the verifier telling you that, hey, this is not good. Okay, so that's completeness. Soundness is the converse, right? So if you don't have a good proof, you don't have the proof, the verifier will never say that, will never let a invalid proof go through. Okay, so the converse. And most importantly, zero knowledge. Okay, so zero knowledge is the idea that unless, except for the statement that I want to prove, you won't get anything else. Okay, so using a very basic example, let's say, is that today you give me a number and be like, for example, 10, okay? You tell me that you want me to show that I know 2 numbers that adds up to 10. Okay, so in my mind, I will be like, well, there's a lot of choice, of course, but well, let's say I pick 7 and 3. Okay, so when I construct this zero knowledge proof, the idea is you will know that I got these 2 numbers, but you will never know that they are actually 7 and 3. Right? So all you know is maybe I know how to add to 10. Okay? So that's the idea. And so this is also very important for a lot of privacy. So that's why zero knowledge proof is related to privacy, and that's because we have this property. But also, most recently, zero knowledge proof has been used for its fourth property, which is what we call succinctness, or in other words, compression. Okay. So the way that zero knowledge proof used is because, well, it's all condensed into one single mathematical statement. And so whatever very complex computation that you're doing, right? So of course I provided a very easy example. But the example of the math problem or whatever problem you're going to solve might be hundreds or 1,000 lines of codes. And it all condensed, when you prove it, it all condensed into a simple mathematical statement. And that actually provides a lot of compression, right? So if I have a huge machine learning model, it still becomes one statement. If I have a very complex computer program, it still turns into one statement, mathematical statement. So we gain a lot of performance gain from that, right? So typically, always, the size of the proof is very, very small compared to what we want to do, what is the underlying computation. Okay, so that is a quick crash course on zero knowledge proof. Now we're going into zero knowledge machine learning. Okay, so now we're going to abstract away from what we just learned, and let's say we assume we already know what is a zero knowledge proof, right? So what is ZKML? The idea of ZKML is that we condense, our computation. So N stands for neural network, right? So a lot of things that we use nowadays in machine learning is neural network. Large language models like ChatGPT is a neural network. Stable diffusion models, DALL-E, all the image generation models is neural network. The idea is, well, we make this neural network into what we call a CK circuit, or you can think of it as a CK program. Okay, so the idea is, once we write this neural network into a CK program, then the prover can use this program to construct whatever proof you want. Okay, so when we say ZKML, typically we already assume that we have that. Okay, so of course there's a lot of complexity that goes into this blob here, but we're going to abstract this away and just think about, okay, let's say we already know how to perform machine learning in ZK. Well, there's actually 3 types of use cases we can go with it. So before we talk about the use cases, there are also 3 types of data that comes in and out of this program. And that's just what we know as traditional machine learning. Of course, you have your input data. So your input data would be something that is dependent on what kind of model you're talking about, right? So if we're talking about a image generation model, so of course the input data would be the prompt, right? Say something like an astronaut riding a horse, or an astronaut on Mars, so that's the input data. Your output data would be the image, right? But it could be something else. If it's an image recognition model, your input data could be your image, your output could be a label, so whatever that image is, right? So when I was doing cognitive psychology, the input data is actually bring scan images, and then the output data is just whatever the person was doing at that point of the bring scan. All right, so this is relatively easier to understand. But then we also have kind of another class of data that goes into this neural network. Typically, we don't really separate it when we talk about machine learning, right? So when we talk about machine learning model weights, it's part of the model. But here, we are separating it into kind of the program, which is the architecture, the design of the machine learning model, and the model weights itself. Okay, so model weights also is an input to this program. And this is usually, in the past, people think that if you give out the model architecture, you immediately disclose everything, right? Because it used to be very easy to retrain your model with some data. So if you have if you know what kind of machine learning model people are running, this is basically trivial if you got data to retrain it. However, with OpenAI and LLM, this has completely changed. Actually, now what is most valuable is the model weights, right? Because training actually takes millions and millions of dollars. So then this data here, the model weights, is actually worth it to kind of get its own place and separate. And you'll soon know why. So let's say we have this kind of program that takes in 3 kinds of data and performs ZKML. There is 3 types of use case, as I said. Typically, you might think of ZK related to privacy, but as I said, one of the most important property is compression. And because of this property, we can actually have the first type of use case, which is no privacy involved. Okay? I just want every single piece of data to be public, but then all I'm making use of zero knowledge is condensation, it's compression. And to make it more concrete, essentially you're getting a verifiable computation, right? I mean, machine learning, even if you're just doing like feed-forward, like inference, it's still going to be very expensive. And typically, you don't expect a journal editor to run the whole computation and check your accuracy, right? So typically, we trust them, right? Or we trust them until someone tries to replicate it or try to redo it. With zero knowledge proof, one way that you can actually make this process more verifiable and also trustless is that you can ask the person who maybe submit a journal paper and be like, oh, I have this great machine learning model that works on this data with 95% accuracy. Well, now you don't have to just trust them. You can verify, right? So it can efficiently compress the computation. So the journal editor just need to run the verifier, which is a very small computation compared to the whole like machine learning model computation. So they can just like verify and check that, okay, yeah, this is indeed true. They do indeed have 95% accuracy. So that's the first type of, first class of use case. The second class of use case is actually we are starting to talk about privacy. In particular, the second class of use case is we are going to keep the input data public and the model weights private. Okay, so it doesn't make sense to keep both of these private, because now then it doesn't mean anything, right? You're just saying that I have some model that does something, and here's the result, right? So that doesn't make sense to keep everything private on the left-hand side. But it makes sense to talk about keeping one of them private and one of them public. And in this case, in the second type of use case, we want to keep the model weights private. So what is the kind of the application of it? Well, one reason could be that you want to protect IP. Right? So a lot of the journals will be like, well, because we can't trust you, then your model has to be completely open source. But if there is this verifiability here with ZK, then that doesn't necessarily have to be the case. Right? You can still have verifiability, but keeping the model private, or at least some part of the model private. Right? So that's first of all IP, right? So it allows for, let's say, further commercialization of this model. And also, at the same time, it can be shared in, reputable journal. And also, the other thing is, it could be that some models actually have ethical implication, right? It might not be, you might have a very cutting-edge model, you want to share the learning, but it might not make sense to completely share the model so that everyone in the world can use it. Right? So that could be kind of one way that the second type of use case that ZKML could be good for. And of course, the third use case is the opposite, right? So just now we talked about the model being private. Well, now let's do the flip side, which is we are keeping the input data private, but the model public. So what could this be good for? Well, a lot of the times, maybe there is sensitive data that we don't want to share, right? So maybe we want to show that there is this public model that everyone knows in this field of, I don't know, biology, psychology, whatever field that the person is in, right? There's already this publicly known model that's known to be very good. And now that I have collected some data, I want to show that using this model, my data gives this result. But I don't want to disclose the raw data itself. Right? So again, then this gives a very provable way of saying that, hey, I have studied this demographic group, right? Or I have studied this like ethnic group. Here's some of the data I collected. I can't show you, but I can show you that I have run this through a very well-known model, and here's the result, right? And then you can trust the result. So that's also a kind of another use case. So kind of like combining all these use cases. I don't think I've put this on the slide, Unfortunately, I totally forgot when I did it. But the idea, actually, when we first talk about ZK and when my PhD advisor used to talk to me about ZKML is that, well, what if we have kind of a data marketplace or model marketplace for academia, right? So it could go both ways. So maybe someone who has a model that they don't want to share publicly, but they will be like, well, you have some public data set, you can actually run it through our model, right? So you give us this public data set, you maybe pay us some money, run this through our model, and we can give you certain result. And I can prove that it comes from my model that I have maybe committed in a previous journal paper. I can prove to you that it's the same model that I'm running. So that's one use case. The flip side of it is, of course, then the other way around, where people will have public models and then they can sell private data, but not in the way that they sell the raw data. But I guess the use case could be, let's say, I don't know, I have collected a bunch of brain scan images of people in the US. And that's very expensive to scan. I might not want to just share directly. The university might not want to share directly. But maybe a lot of people have developed different machine learning models to analyze these kind of images. Right? So instead of sharing my data with everyone so that everyone can try to apply their model on my data, we can do it with a ZK, which is everyone can just give them the model that they want to run through our data. We will run through our data through those models. We will provide a proof that here is the result. Right? So it actually would solve a lot of kind of the collaboration issue, or any of kind of financial concerns, or it actually could speed up the process a little bit before you even kind of need to be required to publicize your data set or your model. So that's kind of the use cases for DeSci for ZKML. And last but not least, just to talk about how to get involved. I think I was very excited to present here because I think actually machine learning is way more common in academia than in the Web3 world. I think pretty much every single field in STEM uses machine learning nowadays. And we really could use, well, I'll talk about this. We really could use some people who are from machine learning. So the difficulty that we're facing nowadays is that we have, well, so typically you know that we have TensorFlow or PyTorch, a lot of these libraries that big companies have developed to perform machine learning. Meanwhile, there are literally, I think, 10 people in the world working on ZKML. But the thing is, we need to transpile all these operations, every single machine learning operations that is out there in these huge libraries, into ZK. Right? Some people who actually know machine learning could be very helpful into just making this kind of tooling that is available for everyone else to turn their model into a CK version of it. So here are two of my libraries that does that. It's in a CK language called Circum, which is actually the easy part. The hardest part is actually the knowledge of machine learning or linear algebra, etc. And the second call for action is, of course, to brainstorm use cases. So everyone in Web3 is very excited about ZK, about ZKML right now, but we actually don't have the first real-world use case yet. Right? So some of the use cases that I mentioned just now are all kind of ideation, or even there are some proof of concept, but no one is actually using or making those use cases. Right? So just to brainstorm how to have different use cases in academia, or eventually building one, could be very helpful as well. Right, so with that, that's the end of my presentation. If anyone are interested in any of the things that I mentioned just now, this is the QR code of my link tree. There's a lot of information there.